In this section, we're going to talk about the least squares regression line. We're going to identify the different components of that formula as well as be able to interpret that formula and then use that to compare predicted data with actual data. So what we're looking at here on the screen is the equation representing the line we would have been creating from a previous section when we created a scatter plot. This is called the least squares regression formula, and we use this line to be able to estimate the average value of our y variable or the response variable with some particular explanatory variable or x. Now, you may already notice that this equation here that's in the center of your screen, y hat equals b1 x plus b naught, looks an awful lot like a formula you would have seen back in an Algebra 1 class called the slope-intercept formula. We're going to use the same type of function here, creating a line, but we're going to identify some different components than it would have been used in a traditional algebra class. The first one we want to look at is going to be B1. Now, B1, you'll notice right here is going to be a number, and it's going to fall directly next to your explanatory variable x. We identify this B1 as the slope. Slope is a rate of change, as it has always been for us, and we're going to use this slope to be able to understand how rapidly that predicted value changes with respect to some x. So slope. When I think about slope, the way that I want to interpret slope is I want to be able to identify the units that we're going to use for x as well as the units I use for y. And I'll show you what I mean about that in a minute. The second component to this formula that we want to understand is the y-intercept. The y-intercept we have identified as b naught or b0 here at the end of our formula. And the y-intercept is where the line that we are creating crosses the y-axis. That's why it's called the y-intercept. And it's going to occur when that predicted value of x is equal to 0. We might think of this as kind of the starting value of our estimation here. And you always want to ask yourself whether or not that is a reasonable value. Is it reasonable to even interpret this y-intercept? You'll notice that the y-intercept is just going to be some number all by itself, so we would call that a constant number. And then your slope is going to be the number being multiplied by your x or by your explanatory variable. So these two values, these two numbers that are going to show up into my formula are in separate locations and represent separate ideas. Finally, y hat. Y hat is our predicted value of y. It's what we are predicting and what we estimate or think is going to happen for any given value of x. When we want to interpret this y, we want to understand it's what we expect, or y hat. When we interpret y hat, it's what we expect my value to be. But that's not necessarily what it is. Remember, you have prediction as well as observed or real world data. Let's see if we can put these concepts into practice here with an example. Here I have a scatter plot that you'll see on the left-hand side of your screen. I believe that this scatter plot is talking about Burger King menu items. You'll notice that if I just want to look at the blue dots here, each one of the blue dots is representing information about actual data. So these are menu items from the Burger King menu, and we are letting protein down here along the x-axis be our explanatory variable, and then fat is going to be the response variable. So we're looking at food items with a given amount of protein and their resulting amount of fat. You'll also notice this red line that is drawn on the screen, and that's the least squares regression line we're going to be working with for this video, for this section. This red line represents, again, our prediction or our estimate of the mean values of these y variables. Here is the formula for that line that we see there. And you'll notice I've purposely put it on your screen so that it is not written in the same form as what we were originally given up here. So I've done that because we want to understand where the slope and the y-intercept are located whenever we see a formula for the least squares regression line. Now, the first thing we want to identify is the slope. The slope is always going to be the number next to your explanatory variable. So in this case, protein is our explanatory variable, and therefore 0.91 has to be the slope. So when I want to think about interpreting slope, you'll notice on the screen one of the ways that I am encouraging you to interpret it is to kind of thinking about slope in terms of my y units per x units. So what I mean by that is slope has traditionally been defined as our y values over x, and we know that from any previous algebra class. If I want to now start interpreting that in terms of the variables in this problem, my y variables represent grams of fat and my x variables represent grams of protein. So I'm going to write down, I'm going to take the time when I'm asked to interpret this to write this type of a fraction down in terms of the problem I'm looking at. My y variables are indicating the number of grams of fat, and again, my x variables are the number of grams of protein. We also know from our formula here that 0.91 is our slope. Now I can write any number over 1 without changing the original number itself. So 0.91 divided by 1 still gives me 0.91. But if I think of it in terms of 0.91 being in the numerator and then adding the 1 to the denominator to the fraction I was already creating here, it helps me kind of organize my thoughts to be able to put this information into a sentence. So now we have 0.91 grams of fat for the numerator and then 1 gram of protein for the denominator. All I did was come in and add the number representing slope over 1. So having taken the time to set up this type of a ratio right here, I'm now ready to move on into a sentence form of interpreting that slope. We might say something like this. Our Burger King items with 1 more gram of protein is expected to have 0.91 additional grams of fat. So that's what I mean when I say we're going to interpret the slope. There's a couple of components to this sentence that need to happen every time we interpret. Number one, I always want to make sure that I am when I'm interpreting, I want to include the 2 variables that I'm referring to. This is the relationship, after all, that we are investigating. This relationship of protein and fat. Protein being the input or the explanatory variable, fat being the response or output variable. So we always want to include those 2 items in our sentence. Then the next pieces that we want to include is by how much do each of these variables increase or decrease. Now we'll notice that our slope here, that 0.91, is positive. That means that as one variable increases, the other variable will also increase. So in our sentence, we have 1 more gram of protein for an additional 0.9 grams of fat. And then finally, what I would say is traditionally we start with our explanatory variable when we're interpreting this. This is why the protein in this interpretation comes first. And then the second part of our interpretation would be the response variable. So we're kind of indicating how much the response variable is impacted for every one unit of our explanatory variable. So this is an example of us interpreting our slope. The second number in our equation, remember that's the 8.4, is going to be the y-intercept. This y-intercept is always going to be, like I said before, this standalone number within this formula. So in this form, my y-intercept is actually occurring right next to the equal sign. We are really used to having our slope, especially from an algebra class, falling right next to the equal sign. But don't fall for that. Just because you have a number next to the equal sign doesn't necessarily mean it's your slope or your y-intercept. You need to determine that based on these characteristics. So if 8.4 is our starting value, it becomes the starting value when our explanatory variable, grams of protein, are equal to 0. So to interpret that, we would say a Burger King item with no grams or 0 grams of protein is expected to have 8.4 grams of fat. When you are looking at your y-intercept, you also want to ask yourself, is it reasonable to interpret the y-intercept? In this particular case, I would say it is reasonable to interpret that. There are food items out there that have 0 grams of protein and yet still contain some grams of fat. Additionally, you can see that we have several points on our scatter plot over here that are relatively close to the number 0 on the x-axis. And so that is also an indicator that would help us to know that it is reasonable to interpret this y-intercept. The second thing we want to discuss before we move into examples later on has to do with this linear model. So one more time, we want to make sure that we understand that this this line that we're creating using technology is considered a model. We sometimes would have called it the line of best fit. In other words, it is a line that is closely related to all of the dots in your scatter plot. And it just gives us the average of our fat in this case for any expected amount of protein from the x-axis. Now, you'll notice that there are a lot of dots on here on our scatter plot that don't line up, obviously, on this straight line. So we want to talk for just a moment then about residual. A residual is the difference between our observed value, so the actual value, and the predicted value, what we predict using our function or our model here. When we have a positive residual, we would say that the observed value is above the average of what we expected. Conversely, if I have a negative residual, the observed value is going to fall below that expected average. Now, you'll notice here that on my scatter plot, it's pretty easy to identify pieces or observed values. Remember, each of those blue dots are the observed ordered pairs for the protein-fat relationship. And it's pretty easy to identify any point here that is either above my line or below my line. If, however, you don't have the ability, let's say, to look at a scatter plot, we can find this above-below average mathematically. What's going on when we actually think about this observed versus predicted value? Let's take this point right here that I circle in green. That point is the observed value for some piece of menu that has, let's see, if I were to come all the way down here, so somewhere around, let's say 31 grams of protein, then the observed amount of fat would be somewhere over here, let's call it 70. So we would have maybe 31 grams of protein with maybe 70 grams of fat. That's the observed value. That's what we really have on the menu. But our model is telling us that if I have 31 grams of protein, I'm going to cross, and I'm kind of putting my line right here, I'm going to cross the x-axis right here where I have scribbled a orange little dot. I predict that for 31 grams of protein, I'm going to have something around, let's call it 38 grams of fat. So you can see that the predicted value of fat for 31 grams of protein is not actually the observed amount of fat for 31 grams of protein on this particular food item. Instead, this line is kind of an average of what we have happening. So we might be able to say that this observed value up here at the top that we started with is above the average for an item with 31 grams of protein. And that's kind of the idea behind what we're going to use these residuals for and how they're related to this line.